Welcome back, friends. Today we're discussing harmonic and ramp excitations. And we're going to start off by looking at our undamped equation of motion. So we had mu dot dot plus ku. And I'm interested in the harmonic excitation, and as the term implies, harmonic has to do with sinusoidal motions. So I'm going to have some sort of amplitude multiplied by a sine wave. Now, with this sine wave, I have a frequency that is labeled omega. I don't want you to confuse this omega with the natural frequency. This is the frequency of excitation. And so when we say natural frequency, we label it omega n, and that equals k over m square root. Okay, so let's keep these two terms separate, and I will explain in a minute or two how these two relate and how, when they're equal, things can get pretty dangerous because we get a condition called resonance. Okay, so if we are thinking about an equation of motion that has the following excitation, and we're thinking about what the solutions are, my hunch would be that the solution would have the same format as well. So if I'm seeing sine omega t in the excitation, I expect that I would see some sort of sine omega t in my solution plus perhaps other terms. So let's look for solutions. So let's say our solution is labeled UPT, and this P stands for particular, which I'll explain in a second what it means. And we're saying that our solution will have the same structure as the excitation, so we have some constant C sine omega t. Alright, so if I were to plug this back into my equation of motion, I would also need to take the second derivative, and that would equal to minus omega squared c sine omega t. Alright, let's plug it back into our equation of motion, this one here, and see what it results in. So we have m omega squared c sine omega t plus kc sine omega t is equal to p naught sine omega t. Alright, now I'm going to change my pen color, and what we can see is that all these signs can be cancelled out because they appear on both sides of the equation. And what I can say is I have c brackets open minus m omega squared plus k closing the brackets is equal to p naught. And if I divide everything by m, what I'll have is c brackets open omega squared omega n squared, and I apologize, I'm dividing everything by k, not m. So m divided by k is 1 over omega n squared plus 1 is equal to p naught divided by k. Okay, so now we can solve for c, and what we observe is that c is equal to p naught divided by k, 1 over 1 minus omega n, and there's a square term here. There it is. Okay, so if you think back to the days of statics, whenever we're dividing our force amplitude by the stiffness component, what that's giving us is some sort of deformation term. And here, because we're studying the role of dynamics, this term here we refer to as amplification factor. So we call this the amplification factor. All right, so let's talk about what this term P means and why we refer to the solution as UP. In dynamical systems, our solutions are typically comprised of the following. So we have a U total for the total deformation, and this is a function of time. We usually have a complementary component, we call it the UCT, and we also have a particular term, UPT. In some books, the complementary term is referred to as the transient phase, and there's good reasons for that, because this term is transient, it passes away. And then we have the steady state solution. That's another way of referring to particular solutions. All right, so what this means is that anytime I have some sort of behavior, which I'm going to draw here, in this case we're referring to harmonic behavior, I'm going to get some sort of harmonic behavior as my solution as well. And this goes on, and there tends to be some complementary solution that gets added to this harmonic behavior that results in an overall response that kind of looks like this. Now, when I have damping in my structural system, this transient behavior or this complementary solution will die off, and so we'll merge to the steady state solution. However, when there is no damping, this will go on, and we tend to get a total solution that looks more like here on the left. Okay, so let's label this total solution and label the red steady state. And steady state is really the solution associated with the excitation, and the complementary is associated with some of the initial conditions and the jolts that go into the dynamical structure and the initial vibration that eventually dies itself out. And so let's think about the total solution for the undamped harmonic case. So we have U, let's call this T for total, is a function of time, is equal to, if you recall, in the last lecture we had our complementary solution for initial conditions have the following form. We had an A cosine omega n t plus B sine omega n t. So that's our complementary solution. We also want to add the particular solution. So we have P naught over K, and we have 1 minus, and then we have this omega term divided by omega n. There's a square here, multiplied by sine omega t. And then when we plug in our initial conditions, we should be able to solve for A and B, and that's what we're going to do next. So UT total, I'm not going to put the T anymore, is going to equal to U naught cosine omega nt plus V naught omega n, brackets open, minus P naught over K omega over omega n. Let's draw better lines. There it is. 1 minus omega over omega n squared, brackets closed, sine omega, and then there's an ender, n t, and then so that's our complementary solution. Then I want to add my particular solution, and that gets me to p over k. Oopsies, I want to draw better lines. There it is. And we have a sine omega t. All right, now something I'd like you to highlight in your head is to distinguish the omega n's from the omegas, and remember where they are positioned. Notice that in my cosines and sines in the complementary segment of my solution, I get omega n's in the harmonic terms, whereas in the particular solutions, or in the steady state solution, I get the excitation frequency, which is a different omega. So keep that in mind. There's good reasons for that. All right, what I want to do next is to think about this amplification factor that we discussed, this term. And to do that, I'm going to introduce an example. So I'm going to take this particular term here, what we're seeing here, and I'll have UPT, which is the particular solution, divided by P naught sine omega t. So I have my output, and I have it divided by my input. And what this is going to give me is my amplification term. So I have 1 over k, 1 minus omega n squared. Okay, now what I'm going to do next is to open MATLAB and plot this amplification factor as a function of omega over omega n squared. So we're going to have a plot that's going to look like omega over omega n, and then I'm going to have this amplification factor, which I'm going to label h. And we're going to see how this really pans out. And by the way, we need to put these absolute signs because we're only interested in amplification and not the sign. So here's our MATLAB, and we have this beta term, which is pretty much omega over omega n. We have the h term, and we're plotting the absolute value of the h against beta. And so let's click run, and this is what we're seeing. Whenever the values of omega is really small with reference to omega n, we will be at an amplitude of 1. And so this amplitude down here should be fairly small. Let's see, there you go. This amplitude here at the vertical axis has a value of 1. And what that means is that whenever I'm applying my harmonic excitation super slowly, I am almost behaving in a static manner. So whatever I feed into my structural system, the amplitude will directly match the output amplitude. And that's typical of static systems. So at 0 frequency, we have statics. As we increase our harmonic excitation and its frequency, we approach a value of omega over omega n is equal to 1. And that means that the harmonic excitation has the same frequency as the resonant frequency, as the natural frequency. And at that point, we're getting massive amounts of amplification. And this is why resonant frequencies are dangerous in structural systems, and we need to either avoid them or engineer them such that they are safe. Okay? Alright, now we're going to do the same thing, but this time we will be addressing the damped case. So we're doing damped case. And again, we're dealing with harmonics. So with the damped case, if you recall, we had mu dot dot plus cu dot plus ku, circle in these dots, and that equals p naught sine omega t. For this step, the solution will be a little more difficult to derive, so I'll skip the derivation and give you the solution. And we're going to see what things look like. We're going to have a particular or steady state solution that has the following structure. We have p naught over k, and we have 1 minus omega n squared. In the denominator, we have the following, plus 2 zeta omega over omega n squared. And then we get a sine omega t. Now, as it turns out, our particular solution will also have a cosine term. And the cosine term will have its own amplification factor, which will look slightly different. There's a minus zeta omega n. Zeta was our damping ratio, so it appears in our particular solution. We have 1 minus omega over omega n squared plus 2 zeta omega over omega n squared. Okay, and then this time we're going to have a cosine omega t. And so we have cosine omega t. All right. Our harmonic solution, or excuse me, our complementary solution will have an exponential term minus zeta omega nt. And anytime you see this exponential term with the negative exponent, it's indicative of a dying response. So we start at a magnitude of 1, and over time this exponential term will take us to a value of 0. And this has to do with the presence of damping. In the last example, we didn't have damping, so the harmonics kept on going and going. But whenever we have damping, those harmonics for the complementary solution tend to die off. And here it is. This is our solution. If you recall, omega d, which is the damped natural frequency, is equal to the undamped natural frequency, 1 minus zeta squared square root. Okay. Now, what if we have a ramp input? What if our input looks something like this? So we have some sort of ramp input that looks like that, where the slope is p naught over t naught. And this is time, this is p of t. So we're interested in ramp inputs, ramp excitations. So in this case, what I want to do is to again go back to the undamped case, because the damped cases tend to have many more terms to take care of, and they just add a lot of complications. But hopefully, with your knowledge, you can, spend the time, sit down, and be able to solve for the damped case as well. So this is what we have. We have a ramp that starts off at time 0, and this is what the excitation looks like. So as it turns out, the solution to this will have the same structure as well. There is going to be the complementary component. Complementary terms always have the omega n. Then there is an A2 sine omega nt. And lastly, our solution will have our particular solution will have the same structure as the excitation force. So we have P naught over K. So it's force divided by stiffness, time over T naught. And if I were to guess what the solution to this would look like, I'd probably have to draw one of these plots. So here's the frame. And given that we're getting a ramp excitation, our particular solution will also look like a ramp, and our total solution will look something like this. And that's just the harmonics associated with this complementary solution. Alright, I hope you found this class useful. We discussed the harmonic and ramp excitations, and we looked at damped and undamped cases. Hopefully, if you have any problems with the derivations, I'll be able to help you. Just leave it in the comment section. I'll get back to you as soon as I can. But these sorts of excitations are fairly generic, and you should be able to find solutions for them in online courses, and through simple Google searches or through a lot of the available textbooks. The one I really like is the ShortProt textbook, and hopefully you can take advantage of those tools as well. All right, I'll see you next time.